Okay, good afternoon. So today we will continue our discussion on number theory. Just a brief reminder, we will have our tutorial this Thursday on the homework 4, and then we will have our exam 2 next Tuesday. Okay, the topic about the exam 2 will be the same as homework 3 and homework 4. Okay, good. Okay, so here, in the following few lectures, when we are talking about number theory, so all the variables that we are looking, they will be representing integers. Okay, so we will talk about integers. We won't handle real numbers, we won't handle rational numbers. Is that okay? So all the A, B, C, N, D, all these variables, they are going to be integers. Okay, so first of all, let me introduce a notation. This notation. So first of all, we say A divides. So we say a number A divides another number B if there exists an integer k such that B can be written as A times k. Is that okay? And then we will write this as A, B. Is that okay? With a stroke in between. So it means A divides B, or A divides B properly. Okay, so for instance, so example. So for instance, 7 divides 63. Okay, 5 divides 15. Okay, but on the other hand, 7 does not divide 10. It does not divide 10. So in that case, we have this like this. So it is like 1 is equal to 1, but then 1 is not equal to 2, so we have a stroke there. Okay, so here it says 7 does not divide 10. And how about this one? How about 10 and then 0? Is 10 dividing 0 or not? Yes, because if you put 10 here and 10 and 0 here, there exists a certain k such that 10 times k is equal to 0. Is that okay? So you write 10 divides 0. But how about the other? How about 0 and 10? 0 and 10? No. So 0 does not divide 10. Okay, so there is actually a very, very special case. According to this definition, we will have 0 divides 0. Okay? Okay? But then this is super strange. So we will not see this here. So forget about this. Okay? But this is important. So any number divides 0, this is important. So we need to memorize this. Okay? Good. Okay. So here, if A divides B, then we will say what? We will say B is a multiple of A. So 63 is a multiple of 7, 15 is a multiple of 5, and 0 is a multiple of 10. Okay. Okay. So we don't restrict these integers to be positive. So we can also talk about negative. So 7 also divides minus 63. 5 also divides negative 15. So negative 15 is also a multiple of 5. Is that okay? Good. Okay. Then we can define what is prime. So we say a number P is a prime so let P to be some number greater than 1. We say P is a prime if and only if 1 and p are the only integers that divide p. Is that okay? So in that case, so 1 and p are the only integers that divide p. So 1 and p are the only divisors of p. So in that case, we will call p a prime. So let us recall. So the first few primes are, primes. So what are the primes? Okay. So 2 is a prime, 3 is a prime, 5 is a prime, 7 is a prime, 11 is a prime, 13 is a prime, 17 is a prime, 19 is a prime. And all the numbers that we miss, they are not primes. So otherwise, so the other numbers are called composite. Okay? But then 1 is an exception. So 1 is neither a prime nor a composite. Is that okay? So composite. So what are the composites? So 1 is not a composite. We will have 4, 6, 8, 9, 10, 12, 14, 15, 8, 16, and so on and so forth. Okay? Good. Okay, now we are ready to talk about a very simple theorem, but it turns out to be very useful. So this theorem is the division theorem. So this is called the division theorem. So division theorem says, so let's say n is an integer, and then let's say we have d is some number greater than 0. Okay. So what happens when n is divided by d? So when n is divided by d, then there will be a unique quotient and a unique remainder. When n is divided by d, there exists a unique quotient q and remainder r such that what? Such that n is equal to qd plus r. And then r is some number between 0 and d minus 1. Is that okay? Okay. So this works for any integer, any negative, 0 or positive integer n. Okay. And then any d greater than 0. So this is so simple, right? Yeah, we all know. But how do we prove it? So how would one prove this? So when 5 is divided by 3, so we can find 5 is divided by 3, then the quotient will be 1, and then the remainder will be 2, right? According to this definition. So when minus 5 is divided by 3, then what will happen? So what will be the quotient and what will be the remainder? Minus 5 is divided by 3. So by this definition, the quotient will be what? Minus 2. Is that okay? And then the remainder will be what? 5 will be 1. Is that okay? Does that make sense to you? So when 5 is divided by 3 and when negative 5 is divided by 3, then we'll have different things. Okay? strange, right? Yeah, but according to this definition, it should be. So 5 can be written as 1 times 3 plus 2. Okay, so in that case, when 5 is divided by 3, then the quotient will be 1, and then the remainder will be 2. Okay, but when negative 5 is divided by 3, so negative 5 is equal to negative 2 times 3 plus 1, right? So in that case, the quotient will be negative 2, and then the remainder will be 1. Okay? Is that okay? So we will, so first of all, there are many Q and R pairs that satisfy n is equal to QD plus R. They're infinite pairs. But when we restrict R to be within 0 and d minus 1, then in that case, there will be a single R that works, and there will be a single Q that works. Okay? So we are going, even though this is a super simple theorem, that we all know this should be correct. Yeah, but let us still prove it. So the proof is by induction. Okay. So we're going to prove it by induction. So let us fix D, and then we assume that we only consider the case that n is positive. The case where n is negative will be symmetric. Okay, so the idea is like this. So the idea is like, so we want to show that for every n, different n, when it is divided by d, there will be QR pairs, and then this QR pairs will be unique. Okay, so we want to show that 0 works, we want to show that 1 works, we want to show that 2 works, and so on and so forth. And after a certain case, we want to show that, so we want to show that we don't know whether this works or not. But then if some of the previous case works, so if this is okay, then this will be okay. Okay, so this is the idea of the induction. And it turns out that it is really simple. Okay, so first of all, we only consider n is positive, or n is non-negative. Okay, so n is non-negative. Now, in this theorem, we want to show uniqueness. Showing uniqueness usually is done by 2 steps. First, we show existence. So there exists QR such that this works. And after that, we show that this QR has to be unique. Okay, so usually we need to form 2 parts. So here, we are going to show this by induction. So first of all, what are the basis case? So by induction, let us say we want to show that by induction, we show existence. Okay, and then this is what we are going to assume. We are going to fix a D, and then we assume n is non-negative. So the basis case is when n is equal to 0, then it exists. When n is equal to 1, so when n is equal to 0, then we will find that 0 is equal to 0 times d plus 0. When n is equal to 1, 1 is equal to 0 times d plus 1. When n is equal to 2, 2 is equal to 0 plus d times d plus 2. Is that okay? So we are going to use n is equal to 1, n is equal to 2, up to n is equal to d minus 1 as the basis case. Then, so the basis case, it works. So far, if you're okay with this, could you please raise your hand? Okay, now inductive case. So assume that for every n is equal to 0, 1, 2, up to k, there exists QR such that n is equal to QD plus R. Okay? Is that okay? Now, of course, here R is between 0 and D minus 1. Now, what happens when we are looking at K plus 1? Now, when n is equal to K plus 1, we have, and then let's say when is equal to K plus 1, and then let's say K plus 1 is greater than or equal to D, then we will have n is equal to n minus D plus D. Am I correct? Is that okay? Now n minus D plus D, but then n minus D is some number that is less than K plus 1. So this is less than or equal to K and greater than or equal to 0. Am I correct? So in that case, n minus D is some number that we have assumed if there is a unique, not necessarily unique, there are QR pairs such that Q times D plus R is equal to this n minus D. Is that okay? So this is, you can write down as, there are some Q, I don't know what Q it is, maybe some Q prime times D plus R. This will be equal to this n minus D plus D. So this is, let's say this is some R prime. So this is equal to Q prime plus 1 D plus R prime, where R prime is some number between 0 and D minus 1. Okay? So this implies that inductive case also work. So by mathematical induction, then all of the numbers greater than or equal to 0, you can show that you can find QR pairs such that n is written as QD plus R. Is that okay? Basically, it is super simple. What does it say? So if I know that 0 to D minus 1, I can have representation Q and R. Then if I add D to each of the number, then of course they will have QR. That satisfies them. Okay? And then, so now we have all the numbers from 0 to 2D minus 1. Then if I add D to the last D numbers, then we will have further more numbers that can be expressed in the form of QD plus R. Is that okay? But then, so far, this shows existence. So this is like the existent part. And then we still need to show uniqueness. So why is the QR pair unique for any n?